explain part 1 in lab 3. So we see here that this is the schematic diagram for part 1, and we came up with this input equation. We got JA to be B because JA is connected to B and KA is always 1 based on the schematic diagram. JB is A0 because JB is connected to A0, and KB is always 1 based on the schematic diagram. And DC is actually the XOR gate, which is connected to the XOR gate. C is connected to the input to pin 1 of XOR gate, and B is connected to pin 2 of the XOR gate. That's why we got DC to be B XOR C. So now let's actually see the state, the inputs of the flip-flops and the next state. So we know that the D flip-flop, when the input of D flip-flop is determined, then the next state will be the same as the D flip-flop. So we get here the DC based on the input equation is B XOR C. So we check here B is 0 and C is 0. So we got here 0. Here I have made the XOR truth table. If we get B and C 0, then the output will be 0. If we get B 0, C 1, we get 1. If we get B 1, C 0, then we get 1. If we get 1 for B and C also 1, then the output will be 0. So let's check the second one, which is 0 0. We still get the D flip-flop to be 0. And here we check that if it is 0 and 1, we get 1, just as the truth table says. Now let's see if it is 1 and 1. If 1 and 1 we get 0, this is the same as the truth table. So now that we determine the D flip-flop results, I said that the D flip-flop results will be the answer for the next state. So if we have D to be 0, then the next state of C will also be 0. If it is 0 for the second one, it will also be 0, and so on and so forth for the rest of the D flip-flop results. Now let's check JB. We have JB to be A0. So whatever result that we have for A, we just flip it and it will be the answer for JB. So if we have A to be 0, then A0 will be 1, therefore JB will also be 1. If we have A to be 1, then A0 will be 0, and therefore JB will be 0, and so on and so forth for the rest of the JB inputs. And we determine that KB is always 1 based on the schematic diagram, so the KB will always be 1 for the of the KB inputs. Now we check JA. JA is the B input. So whatever the results of B, it will be the same as JA. So we have B 0, so JA is 0, B here 0 for the second input, then JA 0, and so on and so forth for the rest of the inputs. Now let's determine the next state of B. We have JBKB to be 1. We first check the previous state of B. We have the previous state of B is 0. So when we check the truth table here, we see that the present state is 0 and J is 1. So when present state is 0 and J1, we have K to be ignored or don't care, and the next state will be 1. So we got here the previous state is 0, JB is 1, KB is 1, therefore we got B, next state of B is 1. So let's take another input, 0 1 1 for example. You got the previous state of B is 1, and the JB is 0 and KB is 1. So we check here the previous state of B is 1, and we have JB is 0. So 1 and 0, this means it doesn't care, and K here is 1. So here K is 1, therefore, so here again JB is 0, KB is 1. The previous state of B is 1, so we get here to be 0 for B, the next state of B. So this is the state diagram that we came up. it will go from 0, 0, 0 to 0, 1, 0, then to 1 to 0, to 1, 0, 1, then to 1, 0, 0, then to 1, 1, 0, then 0, 0, 1, and back to 0, 0, 0. So now let's check the circuit. First, I'll change the clock module to be 1 Hertz. So now it's 1 Hertz, and this is the input, which is the K is always set to 1, and J and the J and K and JA and B is always set to 1 as well. The KA and KB is always set to 1, and the based on here from the XOR gate, one of the inputs of the XOR gate is always set to 1. So now we will set the KA, KB, and one input of the XOR gate to always be 1. So now let's check the loop. Let it restart. So 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, then 0, 0, 1, and back to 0, 0, 0. But if you notice here in the schematic diagram, we have 1, 1, 1 and 0, 1, 1. It's not present in the circuit. So in order to produce 1, 1, 1 and 0, 1, 1, we have to wire KA and KB to a switch and take them as low. But for the usual operation, we'll always set them to high. So for this case, we'll set KA and KB to 0. So now let's change it to 0. So now we only have one input of the XOR, which is always 1. So if we check here, it always goes from 1, 1, 1 to 0, 1, 1, 0, 1, 1 to 1, 1, 1. So the loop always goes from 1, 1, 1 to 0, 1, 1. So we actually determined the missing part of the loop. So that's it for my part. So for the second part of part 1, we are supposed to force a particular value for the transient states to be checked. So the first special case is 0, 0, 0 to 0, 1, 0, then to 1, 1, 1, and back to 0, 1, 1, and it keeps loop forever from 0, 1, 1 to 1, 1, 1. So let's try it in the circuit. So first it is 0, 0, 0. Now it will go from 0, 1, 0 to 1, 1, 1, then to 0, 1, 1, then it will keep looping forever from 0, 1, 1 to 1, 1, 1. Now let's go to the second state, which is 1, 0, 1. It will keep looping forever in 1, 0, 1. So we set KA and KB back to high. So this is 1, 0, 1. So now we set KA and KB back to low. Now we try the 1, 0, 1. It keeps looping forever in 1, 0, 1. So now the third special case will be 0, 0, 1. So we set KA and KB back to high. Then we go to 0, 0, 1. So this is 0, 0, 1. We set KA and KB back to low. So now we try. It keeps looping forever in 0, 0, 1. So the fourth. Then we go to 0, 0, 1. So this is 0, 0, 1. We set KA and KB back to low. So now we try. It keeps looping forever in 0, 0, 1. So the fourth state will be 1, 0, 0 to 1, 1, 0, and 1, 1, 0 to 0, 1, 1, then to 1, 1, 1, and it will keep looping forever from 1, 1, 1 to 0, 1, 1. So we set KA and KB back to high. And we go to 1, 0, 0. So this is 1, 0, 0. We set KA and KB back to low. Then we check the state. So this is 1, 0, 0. It goes to 1, 1, 0. Then from 1, 1, 0 it goes to 0, 1, 1. From 0, 1, 1 it goes to 1, 1, 1. And it will keep looping forever from 1, 1, 1 to 0, 1, 1. So that's it for part 1. Thank you.
And today I'm going to explain question 2 part B, which is this one. Implement the function FABCD with its minimum terms using an 8 to 1 multiplexer and a single gate. So over here this is the Carnot maps, and we simplified it into an equation, which is this. So as you can see here, this is a minimum term, so it's SOP, that means these are ones. So if you see here, it's 3 is 1, 4 is 1, 5 6 1, 8 is 1, 10 is 1, and 11 is 1, 13 is 1, and 14 is 1. So, and we have used a 151 IC, and we have used a double IC for the NAND gate. In order to get the values of I0 to I7, we will look at D to look at the output F. So over here, D is 0, F is 0, D is 1, F is 0, so I0 is 0. So over here, D is 0, F is 0, 1, D is 1, F is 1, so I1 equals to D, and D is 0 and F is 1, so D is 1 and F is 1, so I2 equals to 1. So D is 0, F is 1, D is 1, F is 0, so I3 equals to D0, and D is 0, F is 1, and D is 1, F is 0, so I4 is also equal to D0. And over here, D is 0, F is 1, D is 1, F is 1, so IF equals to 1. And D is 0, so F is 0, D is 1, and F is also 1, so I6 equals to D. And finally, D is 0, F is 1, D is 1, F is 0, so it's also D0. And we implement this truth table on the board. So first, all of them are 0, so F is 0. Now in the second one, D is 1, so F is still 0. And the third one, C is 1, F is still 0. And then on number 3, C and D is 1, F is 1. And then B is 1, all the others are 0, so F is 1. And now the fifth one, B and D are 1 and others are 0, still 1. And now B and C are 1, it's still 1. And this A is 1, others are 0, it's lighting up, it's 1. And number 9, A is 1 and D is 1, it's not lighting up. And then 1 0 1 0, it's lighting up. And then 1 0 1 0 double 1, it's still lighting up. And then double 1 double 0, it's not lighting up. And then double 1 0 1, it's lighting up. And then triple 1 0, it's lighting up. And finally, when A B C D is 1, it's not lighting up. So now I'm going to explain part 2C, which is implement the function FABC max terms 01367 using a 128 decoder and a single gate. So max term is POS, and decoders generates all minterms in negative logics. So using the Carnot map, we made the equation for F0, which is this, and using De Moivre's theorem, we got F equation, which is this. So in this truth table, this is max term, so the values for 01367 are zeros. So 0 for 0 is 0, and 1 is also 1 is also 0, 3 is also 0, 6 is also 0, and 7 is also 0. And for this one, we use the IC138, and we use a triple NAND gate 74HC10IC. So we'll implement this on the board. So A, B, C is 0, output is 0. C is 1, others are 0. The output is 0. And B is 1, others are 0. So the output is 1. And then B and C is 1, others are 0. So the output is 0. So A is 1, others are 0. Output is 1. A and C are 1. The output is 1. A and B are 1. The output is 0. And when all of them are 1, the output is 0.
And I'll explain part 3 in lab 3. So here we have the truth table for part 3, and we come up with the hazard, which is 111 and transition to 101. So this is A, this is B, this is C, and this is A, B, and C. So the difference, it goes from B, which is 1, it goes to 0. This is where the hazard occurs. So this is the schematic diagram for our hazard. And we are using 3 inverters, which is this part. And we used 3 inverters in order to produce the hazard, since one inverter wasn't working. So now let's go to the circuit. We are connecting A and C. We are connecting A and C to the switch module, and we are connecting B. We are connecting B to the clock module in order to produce the output on the DSO reading. So this DSO reading, it is supposed to be all 1, but because of hazard, it occurs to be 1 to 0. So it's supposed to be all 1, but when it comes from 1 to 0, it drops. That's why there is a hazard occur. In the next part, we will explain how to eliminate the hazard. We added another gate, which is the AC, in order to eliminate the hazard. We used AC to control the transitioning between 1 and 0 in order to make all the output as 1. So that we're using 3 triple NAND gates, since we are adding AC to the input. So we have 3, 4, 5, and 6 as the output. So when we go to the circuit, we connected the AC, which is the added gate, to the switch module, and we left everything else as the previous connection for the hazard part. So for the output here in the DSO reading, we got everything as 1. That's because of the added AC, which holds the transitioning between 1 and 0. So that's it for my part. Thank you. We are supposed to find another hazard, which is the hazard 0, but we are not finding the hazard 0 because we are focusing on the POS. We are focusing on the SOP. So SOP is for the hazard 1. That's why for this part we are using hazard 1 instead of hazard 0.